Thank you for the introduction, and I'd like to thank Wen Ki for the invitation and organizing this. Good to, I need to echo Guosan that it's good to see a lot of old friends, but with a lot of dark hair still. So I'm going to talk about an interesting project I did with my student. So this is actually serving as a disclaimer that the student's doing all the heavy lifting. If there's some question that I can't answer, don't blame me, because student is just too good. So, and the second disclaimer is that it's like 2 a.m. in New York, so if I start talking gibberish, you know what happened. So I just need to stand on my 2 feet. So, but anyway, so this is the title. This is the a brief outline of my presentation. So the highlight of the presentation will be to present a method which I call least square recursion with eigenvalue constraint. And so this is a very brief outline, motivation, some review of the theory, and then the method, and then some simulation discussion. So hopefully we can spend more time on questions and answer. It's an interesting project. So let's start with a data set from a clinical trial of irinotecan, the drug for cancer patients. And the innovation in this trial was that the investigator developed some sort of biomarkers based on baseline phenotype that they can use to predict drug clearance. So the idea is that the higher the drug clearance is, you can dose patients at a higher dose without causing them toxicity, right? So the whole point is to test whether this biomarker works. So on this figure, you see the dotted line. That is what was used to give irinotecan dose to patients according to this biomarker. So the x-axis indicates the biomarker, which I call predicted clearance. And so if you believe the single compartment model in PK theory, and the target of this dosing algorithm is to dose a patient so that they'll achieve a target AUC of the drug concentration at 22.157. I don't know where this number came from, but this is something that they aim at the trial. And if you believe that the single compartment model is correct, that the predicted drug clearance is a perfect biomarker for the actual clearance, then we should treat patients according to the dotted line. So, and in this study, there are 40 subjects. Half of the subjects were actually treated according to this dotted line. So you see there, each dot corresponds to a patient with the predicted clearance and then the dose given to the patients. And there should be 20 dots, 20 circles along the dotted line. So this is half of the study. The other half of the study was, of the study was given to the more conventional dosing algorithm based on body surface area. So the idea is that the bigger you are, you can take more doses, right? So again, the body surface area formula still try to target people who can absorb the drug better with higher dose. So, and then you see there are about 20 dots that's off the dotted line. So those are the patients treated according to the body surface area formula. So this is the data and what was done in the study. So at the end of the trial, so the purpose of this trial was to validate that the dosing equation is a better way to prescribe the irinotecan dose in terms of achieving the target AUC at 22.157. So this is the goal. And but after the study is completed, we did something relatively straightforward. We fit a least square recursion and least square estimation. So, and then use that to estimate what is the optimal dosing equation. And then it turns out that the solid line is what we should have prescribed dose to patients in study. So we see that if we treat, well, the solid line itself is an estimate based on 40 data points. But if we treated this as the true dosing algorithm, we noticed that most patients in the trial were underdosed. So this is sort of one of the motivation for early dose finding is to try to treat as many patients as the true dose, so to speak. as possible. So this is a sort of the motivation for why we want to think about how is there a better way to improve the dosing estimation. So first, improve the estimation of the dosing equation, and to also improve the dosing of study subjects within the study. So these are the dual objectives usually seen in early phase trial. It's not only about estimation, but also about treating the patient well. So let's do something very straightforward. Well, statisticians need a model, and this is the simplest model that we can imagine, right? So in this talk, Y is the outcome. So in this example, everything's on log scale. So Y is the area under the curve, the drug concentration in the blood, and X is the dose, Z is the biomarker. So in this example, we have a very specific motivation that Z is a biomarker for drug clearance, but if you are into more genomic types, it could be any type of biomarker that you can imagine. So, but because of this particular application, we chose this linear model because if we believe that, again, under two assumptions, if the biomarkers is a perfect marker for the clearance of the drug, and that the single compartment model is correct, then this linear model is actually cover that single compartment model, and with very specific value of alpha, beta, and gamma on the model parameter. And with the data, we actually test that the single compartment model is not quite right. So we managed to reject the null hypothesis that the biomarker that we use is a perfect predictor of the drug clearance, or that the single compartment model is correct. So of course, we can't tell which one is wrong, but at least the investigator believe that the dosing equation does its job. It doesn't, at least not perfectly. So the goal is really to find a dosing equation, which is defined at the bottom of the slide. So under the linear model, if the goal is to, for each biomarker value, we want to find a dose so that the expected outcome equals to a target value, T0, 22.157, that funky number that I showed you. So this is a number that's difficult to remember, but I think if I repeat it often enough, you remember 22.157. So that's the number that we want to target in the study. So if this is our objective, with this model, it's not that difficult to find that this is the dosing equation that we would like to estimate. So we're now estimating a function, right? So theta is the estimate that we like to we want to focus on, which is a function of the biomarker. So for each biomarker, we want to find theta so that that would be the dose. So this is the objective of the study. And in the area of dose finding, remember there are two objectives. One is estimating theta. The other is to try to dose study subjects as close to theta as possible during the study. And the way to do it is to use some sort of recursion or continuous assessment methods. So something that Guosheng had talked about. So it's sort of a very generic approach in dose finding in clinical trials. I'm using sort of the simplest example so as to illustrate the concept. And if you don't like least square estimation, think Bayesian. You can do use whatever method that you want to estimate. But the idea is that our goal is to estimate this function, right? So, and also to treat patient well during the study. So the idea is that during the study, we just repeatedly estimating the model parameter alpha, beta, and gamma. And at an interim, for the next patient who comes to the study, let's say we get an estimate of the dosing equation after the first I subjects. When the I plus one subject arrives, we get the we measure the biomarker value, and then we treat that subject according to the most current estimate of the least square function. So this is a least square recursion. The concept is actually not new. The concept of least square recursion appeared in the 70s, and this is a reasonable way to do it. And in practice, sometimes we like to truncate so that we don't want to treat beyond certain dose level of the drug. Well, this is very straightforward, except that it doesn't work. Otherwise, the talk would have been stopped here, and then everyone can have like 45 minutes break. And so this is a simulated trial under which the solid line is a true dosing algorithm, and but it's a simulated trial in 40 subjects. And as it turns out, most of the subjects in the simulated trial were treated along the final estimate of the dotted line. So, well, it's fortunate that in this case, we knew what the truth is, but imagine that if this is a real study where we don't know what the solid line is, and we would be led to believe that we got pretty darn good estimate because of the fact that everyone is treating according to some final estimate. And then we tend to believe that self-consistency is consistency, but obviously that's not true. So, so this is sort of the first sort of intuitive way to approach the problem. It's a reasonable way to do it, but it really doesn't work. There are many ways we could fix it. There are actually a lot of quick ways to fix it, but the idea is to go back to the fundamental reason why it fails in the first place. So in the model that I just described a few slides ago, is a simple linear model, and we wonder that least square estimation is consistent, right? And but it is true only under certain assumption on the design matrix, right? And if the design matrix itself is a fixed design matrix, so this is usually one of the, because it's so common that we use least square estimation, we almost always overlook the assumption required for consistency. So if it's a fixed design matrix, we require that the smallest value of the eigenvalue of this matrix M transpose M to go to infinity, right? So that's the consistency condition for least square recursion. So this is a fundamental problem with adaptive design in that in adaptive design, the next design point depends on the previous outcomes for which we have no control of. And as a result, there's no guarantee that this consistency condition will be satisfied. So this is problem number one. The second problem is that in adaptive design, we actually would require a much stronger assumption for consistency than the smallest eigenvalue converge to infinity. So, and again, this is not a new theory. It actually was discussed in a seminal paper in the 80s by Lai and Wei. So we are actually in a regression for stochastic, a stochastic regression problem under which the least square estimation will be consistent only if this condition holds. So, so this quantity, which I'm going to call eigenvalue ratio, although I know that it's not exactly ratio because there's a log in the numerator. But so again, lambda min is the smallest eigenvalue of this M transpose M, M being the design matrix. Lambda max is the maximum eigenvalues. And so if it were a fixed design regression problem, we require that lambda min to go to infinity as n increases. But because we're dealing with stochastic design, we need lambda min to go to infinity as a fast at a faster rate than just you can go however fast you want to go. So basically, the idea is that you want this ratio to converge to 0 as n increases. So that's a sort of classical result in stochastic regression, which has been sort of overlooked in adaptive designs in general. So for some reason that I'm not quite sure. And just to verify that, well, we cannot prove consistency, but obviously we can prove inconsistency by giving a counterexample, right? So this is the trial result that I showed you in the simulation. And so this is plotting the eigenvalue ratio against the subject. So we see that there's a huge drop in the eigenvalue ratio at the beginning, but then it plateaus around 5,000. So it's not going to 0 soon enough anyway. So, so this could explain why we have this self-consistent problem. we're not converging to the correct dosing algorithm. So we have a reasonable method that seems to fail a condition. So the way that I propose to fix this is to just force the consistency condition to be true so that I don't even need to prove consistency. So that's the method that I try to propose. And so I'm going to apply this condition, or now C become constraint, not a condition. So I'm going to apply the eigenvalue constraint onto the least square recursion. So if you remember that this theta hat is the least square estimate. So with the method without the constraint would treat the next subject with biomarker Z n+1 at this dose, right? But again, theta hat, if giving patient theta hat will not guarantee us to have a consistent design matrix. So what we need to do is to simply to find the closest dose to this estimate, subject to the constraint that this eigenvalue ratio will be bounded about by a sequence R, and this R is pre-specified so that we know that you will force eigenvalue ratio to go to 0. So we've basically forced it to treat patient at the design point that will satisfy the consistency condition. So we don't even need to do something fancy. All we need to know is to do a least square estimation, and then to know how to calculate eigenvalue. So these are the only two things we need for the design. Very simple. And we're calling it theta tilde. Well, not that simple. There are three practical considerations when we use this least square recursion with eigenvalue constraint. One is that it is a model-based design, right? So and when we don't have data, we don't have estimation for the model parameters. So we need to do something called initial design, which is relatively straightforward in this context because in this trial we do have some sort of conventional way to give to dose patient, which is based on this body surface area. So the idea is that we start the trial dosing patient according to the body surface area, and as long as we get some sort of stable estimation of the least square, then we switch to the model-based method. So this is the first step. The second component is called coherence. Guo briefly mentioned it. So the idea is that we're not treating mice or any animals. So coherence is a sort of a ethical constraint that makes sure that if the current subject has a toxic outcome, and then in this context, if the current subject has a toxic outcome and a lower clearance than the next subject, we want to make sure that the next subject is not going to get a dose higher than the current subject, right? And then on the other hand, if the current subject does not have a toxic outcome and has a higher clearance than the next subject, we should not treat the next subject as a lower dose. So basically, this is sort of logical constraint that makes sure that we are not dosing patient unethically. So this is the second, again, practical consideration. And as far as the methodology is concerned, the biggest obstacle is in identifying this sequence. Remember that the whole idea of least square recursion using this constraint is that we force the design points to be placed so that the condition of consistency will hold, right? So, but how far should we force it to go down to 0? There are really many choices. I just use something relatively, it looks right in the literature in the form of this. So this will be the form of the Rn that we need to pre-specify for the design before we do the least square recursion with eigenvalue constraint. And so C here is the eigenvalue ratio based on the initial design. So that would be sort of set as the initial starting point. And to give you a perspective, it were a completely randomized study under which the consistent condition will hold. That will correspond to a value of, let me see, that will correspond to a value of delta 1 equal to 1 and delta 2 equal to 1. So that will be the fastest rate that R can go to 0. But that would also correspond to a completely randomized design, meaning that the subject during the study will not benefit from what we learned during the study. And so the question is, how do we choose deltas in order to make sure that we get good estimation as well as good dosing property of the patients during the study. So the way to do it is by what I call a design calibration steps. It's very straightforward. We just iterate the 2 parameters, delta 1, delta 2, the 2 design parameters. And then for each pair of delta, we define a least square recursion with eigenvalue constraint. And so for each design, we just run simulation by under 10,000 scenarios. And the scenarios are generated from the possible distribution of the data that I showed you at the beginning. And the step 3 is to pick the pair of delta that correspond to the minimum average loss. So we do need to define some sort of loss function, which is given here. So again, it's nothing too complicated. It's because we want to strike a balance between estimation and dosing cost during the study, right? So the loss function is actually reflecting that. So we have this is similar to integrated error in estimation of theta z. So essentially, it's a squared error loss function, but we need to integrate with respect to z, because now with respect to the distribution of z. So this will represent the estimation property, the estimation error of the procedures. And then dn is also a squared error loss for patients who are treated during the study. So this will be, so for a study with n subjects, so this is the total error, total squared deviation from the ideal dose of that patient. And so this is a loss defined per simulated trial. And we ran 10,000 trials, so we sort of use the average to estimate some sort of risk. And again, so the risk, it represents the dosing cost on average of the pair of delta imposed on the study subject, and this is sort of the mean squared error for the estimation. And in order to define this risk or cost functions, I think C for cost, we need to define kappa. Kappa is, so if we have a big kappa, we'll place more importance on estimation. If a small kappa, we'll place more importance on the dosing cost, right? So, and so a practical way to do it is, I would imagine that this is in a sense, a phase 1 study, and in this context, and it's about 40. If we sort of imagine that there's a next step of phase 2 trial to be certain sample size, I would choose kappa so as to reflect that kappa n will be equal to that future trial. So this is how we specify the loss and hence the cost function for each pair of deltas. So the question is, we want to choose a pair of deltas so as to minimize this cost function. And so in this figure, each dot corresponds to one pair of delta. And we see sort of the general trade-off that unfortunately there's no free lunch, in the sense that the ideal case is that we have a dot here, but it doesn't work out that way. So we see that in general, in order to have a small mean squared error, we need to induce a lot of costs on the patient. So which makes sense, right? So the best design, if you just care about estimation, the best design, I mean, there's a lot of optimal design theory that you can, essentially, you just need to spread out the design point so that you can get the best estimation. There's nothing new in statistical theory, and likewise, in order to reduce the within dosing costs, we just don't have the ability to estimate at the end. So there's a clear trend of trade-off. And So that's why we need to have some sort of quantitative definition on how to pick one. And so based on a cost kappa equal to 5, this is the sort of sweet spot, how we choose the optimal deltas. And of course, the argument here is that if you give a different loss function, you get a different dot, right? But yeah, we have to choose something. We cannot choose, not choose anything. But no matter how you choose a loss function, if you sort of imagine that if you just draw like a tangent, it'll be either this dot or this dot or this dot. So these are the only 3 possible dots, regardless of how you choose a loss function. So it's not like that the loss function give you totally different result of delta, but we decided to use this pair of delta and to give you a perspective of what this delta means. So it means that R will converge to 0 at a rate of square root n and log n. So this is actually is a reasonable looking convergence rate for in the literature. So just to show you, so this I've shown you before, the simulated trial that didn't work, and this is the corresponding eigenvalue ratio for the same 40 simulated subjects. So you see that at least in this particular simulated trial, it gave us quite a bit of improvement in terms of the final estimation. So the dotted line here is the final estimate of the dosing algorithm. The solid line is the truth. So it gave us a much better estimation, and also with a reduction of the dosing cost from 1.8 to 0.82. And to verify that the eigenvalue constraint is working, we see that the eigenvalue ratio drop sharply here, keep dropping, and then you keep dropping. But this should not come as a surprise because we force it to go to 0, right? So that's by design. So this is based on one simulated trial. You can always find trial that works. So let's look at the more extensive simulation scenarios. So we consider 7 different scenarios, actually 7 times 14 different scenarios, where y is generated according to this model. G is some sort of link function, and so under scenarios 1 to 5, we have the identity link. So remember, the working model is a linear model, right? So under scenarios 1 to 5, the working model is also a correct model. Whether under scenarios 6 and 7, G is something else. So I forgot what they are, but basically, I like using model-based method, but I think it's important to also run simulation under model misspecification so that we know that even if the model is off, it's not that off. So we have 2 scenarios where the model is misspecified, and is we have a normal noise, mean 0, standard deviation 0.26. I believe this is based on the data that we got, and we look at 2 different values of the slope. So we have 14 scenarios altogether. And we're comparing 4 methods with sample size of 40. It's the original least square recursion without the consistency constraint. So this is the second method is the method that we propose, least square recursion with the eigenvalue constraint and body surface area formula, and then the dosing equation in the original proposal. So these are the different dosing algorithms under different scenarios. Remember, we have 2 slopes, 2b. So you see that we try different scenarios. Although the calibration is based on an ensemble of scenarios, but we want to look at operating characteristics under fixed scenarios. So we represent a wide range of things, and just some quick numbers. So again, these are the 4 methods, and this column indicates the dosing cost to patient during the study. This is sort of a mean squared error for estimation. So for these 2, small is good, and the efficiency is simply the sum of the two or sum of the square of the 2. No, actually, sum of the sum of the two, and then use the least square recursion without the constraint as reference. So if you just look at the efficiency as an sort of overall metrics, we see that the eigenvalue constraint method improve over the other methods substantially. Sometimes improvement is slight, but at least it's not doing worse. And so this is something that we sort of expect to begin with. And what I did not anticipate was that the efficiency improvement was quite substantial. Like sometimes it's like 30 or even close to 40%. And so this is so one single metrics. But if you want to break down the efficiency into what happened, just to compare between the least square recursion and the one with the constraint and the one without the constraint, remember that the motivational constraint is to make sure that we can estimate. We can do a good job in estimating the curve at the end of the day, right? So so what we would expect is that the mean square error due to the method with the eigenvalue constraint will be smaller, which is true in all cases. And this actually contributes to the improvement in efficiency most of the time. So this is not surprising. This is what we set out to do by applying the constraint. It's all about estimation. What was somewhat surprising is that after applying the constraint, you actually improve the dosing cost during the study. So that's sort of counterintuitive. So the whole idea of using least square recursion without the constraint is that it's sort of what we call the best intention design, right? So based on whatever you have at this point, you treat the next patient at the best dose that you can come up with based on the current data. And so based on that, you would expect that by applying the constraint, we're sort of forcing to dose patient away from the optimal based on the current data. So we would expect that will improve the estimation efficiency at the expense of the patients in the study. It is true in some of the situation, we see an increase in the dosing cost. It's not true in other cases. So, so this is sort of counterintuitive in the first place, but at the end of the day, I just remind myself with the simulated trial I showed you earlier that we all tend to think that self-consistency is consistency, right? So the best intention of course, we like to give them the best, but it may not be good enough. So by treating the best we have does not guarantee that we're treating them at a good dose. So that explains why that even though we apply constraint, try to force people away from supposedly the best, we're actually not doing harm. We're actually doing better in terms of both dosing costs and the estimation. So this is actually an interesting thing to chew on. Yeah, so more simulations, similar numbers. So we see that the improvement by the eigenvalue constraint here is not usually big. So it's like 7%, 10%, parity. Sometimes it can be 42. So, but we see a general trend that the improvement mainly come from improvement in the estimation. On some occasion, we'll reduce the dosing cost. In some occasion, we'll increase. So there's no guarantee in that. But in general, it works. So these are the two scenarios where the models are misspecified. And if you look at the magnitude, we see that there's a slight higher. Everything is larger here using the least square recursion because the models are misspecified. But the key here is that is still the relative performance of the two methods. So in this case, with the eigenvalue constraint, we still do better, even under model misspecification. So this is something that I probably need to spend more time thinking what's behind it. But but it doesn't change the general message that the applying eigenvalue constraint does not will improve the efficiency. And now, if you look at the other two methods, the body surface area, for some reason, these are really poor design. So in terms of efficiency as well as dosing cost. And then the equation dosing algorithm in the original paper, because it's deterministic, it doesn't give us any information to estimate the curve at the end of the day. So we can even estimate, perform estimation at the end of the trial using the equation arm. And so the way, there are many ways we could view the eigenvalue constraint. One way to view it is that to try to steer away from being greedy. So a lot of those finding methods in the literature is what we call best intention, greedy methods. So the idea, again, the idea is that we use whatever data we have, we estimate the best dose we can, we treat the next patient at the best dose. This is the idea. But what eigenvalue constraint is, in a sense, you can view it as a way to also have some consideration for the information in the estimation of the parameters, right? So, so there are quite a few methods out there. You could think about this. You can use a model-based method that maximize a trade-off between the best intention and also some sort of information matrix, right? So that's actually an idea that has been explored before. What's new here, and which is makes the whole thing very practical, is that eigenvalue constraint depends only on the eigenvalue of the design matrix. It does not depend on model parameter, right? Because if you want to estimate information matrix, you want to maximize the information, you still need to do some estimation, right? So, but eigenvalue of a design matrix is eigenvalue of design matrix is free of model parameters. So, and it's so easy to calculate. You don't need to do any estimation. And the good thing about this is I show you an example where we talk about linear model using least square recursion. The theory has been extended in the 90s for generalized linear model. So if you're binary endpoint, which is very common in those finding study, you have a logistic model, you can use the eigenvalue constraint to make sure that it's consistent. And if, again, you don't have to stick with least square estimation. If you're Bayesian, it works for Bayesian estimation too. So the eigenvalue constraint actually gives you a lot of flexibility in choosing the model, the estimation method, and also the dose finding problem that we're dealing with. I showed you one application very specifically on individualized dosing algorithm, but imagine we have a dose combination, the problem that Guosheng had talked about. If we have an outcome regress on two agents, the eigenvalue constraint theory applies. So you could use that for dose finding drug combination problem. If you have a if you are not monotone dose response rate, as long as you know some sort of what F, the form of F is, you can apply the eigenvalue constraint to make sure that you get consistent estimation. So the application is very broad here in terms of using eigenvalue constraint. And so the tricky part is really to specify the ratio, the eigenvalue ratio sequence R. And in this application, we use simulations. We're fortunate enough to have data so that we can draw simulate data from the posterior distribution. But this is actually something that requires more thought, how to choose in general. And the other consideration for this is the choice of the model. We consider a linear model, again, simply because it extends from the single compartment model. And if you want to choose other model, as I showed you in the previous slides, you can actually use it on other more complicated models. So, and so this is the reference, and I believe this is my last slide. And thank you. Also, outcome is why AUC. AUC is the area under the curve of. Oh yeah, so I probably should have explained the outcome better. So, so this is the outcome is the PK parameters. So basically, you draw blood from the subjects. It is a measure of the drug concentration, right? So, so it's a continuous outcome. Is it the yeah? So, yeah. So and so the idea of this original innovation is that if you knew what the drug clearance is, the single compartment model says that your AUC will be equal to your dose divided by drug clearance. So this is what the single compartment model in PK theory will implies, right? So the innovation of this study is that they come up with a biomarker that they think is a perfect predictor of clearance. And because of that, you want a log scale. Log clearance, right? And then because the goal is to find a dose for each drug clearance so that this is equal to log of 22.157. So basically, the dosing algorithm in the equation arm says that doses at log 22157 plus log clearance. So 22157 clearance. Okay. So if we knew drug clearance, and since this is a target, so the ideal dose would be simply 22.157 multiplied by clearance. But the problem in this case is that first, we need to believe that this model is correct. Second, we need to believe that the biomarker is a perfect marker of drug clearance. In which case, but in this case, we don't know which one is false, but we know that, but based on the data, we realize that this is not quite correct. So the outcome here, Y, will be AUC. Yeah, so I probably should have explained the problem better. So.